Hello everyone. So in the previous session we have solving the problems on Laurent series. So here is the last problem based on the same concept, that is we have to expand the given function f of z by using the Laurent series expansion. So here also three sub questions is given. Anyhow, before solving the sub questions, first we have to rewrite the given function by using the partial fraction. So let us consider a function f of z is equal to 1 divided by z into z square minus 3z plus 2. Now we can note that if you simplify this quadratic equation, you will get z minus 1 into z minus 2. You just simplify this quadratic equation, apply any of the method, that is factorization or by formula method, you will get this solution. Now let us consider the term. I'll just split this term by using the partial fraction. So how can I write this? I can write this as a divided by z plus b divided by z minus 1 plus c divided by z minus 2. So as usual, problem will not be sent in the group. You just copy down by seeing the video. Afterwards, whatever the theorems I will continue, I will send you the notes of the same. Fine. Now how can I write this as a into z will cancel. So what you left with z minus 1 into z minus 2 plus b into, again z minus 1 will not be there. Remaining is z into z minus 2 plus c into z minus 2 will not be there. So you will get z into z minus 1. Now let us substitute the values for z. So let me give z is equal to 0. So b will not be there, c will not be there. You will get the value of a. So a into z is equal to 0. So you will get 0 minus 1, 0 minus 2. So after simplification you will get a into minus 1 minus 2. So a is equal to 1 by 2. Similarly, let us substitute z is equal to 1. So when you substitute z is equal to 1, a will not be there and c will not be there. You will get the value of b and it is given by 1 minus 2. So 1 is equal to b into 1 minus 2 is minus 1. So b value is minus 1. For partial fraction, you are familiar with that. Now let me substitute the z value as 2 so that you will get the value of c. When you are going to substitute z as 2, a and b will become 0. So you will get 1 is equal to c into 2 minus 1. So 1 is equal to c into 2. 2 minus 1 is 1. So you will get c as 1 divided by 2. So once you obtain the values of a, b, c, so I can write this function 1 divided by z into z minus 1 into z minus 2 can be written as a is 1 divided by 2z plus b is minus 1. So I'll just write minus here, minus 1 divided by z minus 1 plus c is 1 divided by 2 into z minus 2. Now we can expand the function. Now look at the first sub question, what it is. It is z less than 1 and z greater than 0. So I can write this as f of z is equal to, I'll just if you want you can rearrange, or else let me simplify. For the first sub question I can write this as 1 divided by 2 into z plus I can write this as z minus 1 power of minus 1 plus 1 by 2 as it is. Now let me take 2 as a common term. Why? Because z is less than 1. So when you get 2 as a common term, you can write z by 2 minus 1. Fine. So 1 divided by 2z. So if you simplify the problems, you will get an idea that which term we have to take the common factor. It is up to you. You can remember as and how you want. So z minus 1 power of minus 1 will be 1 plus z square plus so on. Right? Plus 1 divided by 2 into 2 is 4. So again I can write this as z by 2 minus 1 power of minus 1. Fine. Now let me simplify one more step. F of z is equal to 1 divided by 2z plus 1 plus z square plus so on plus 1 by 4 into x plus 1 minus, it should be of the form 1 minus x power of minus 1. So let me take minus as a common term. So when you take minus as a common term, you will get 1 minus z by 2 power of minus 1. Clear? Then I can write this as 1 plus z by 2. It is plus 1 plus z by 2 plus z by 2 whole square plus so on. Either you can keep this, or if you want you can take the common terms of z and you can simplify if you want, or else you can keep like this only. Next, look at the second sub question. I'll just solve the second sub question. So the second one is 1 z less than mod z less than 2. So this is the second question given to us. Fine. So this is the solution for the first one. Now I am solving the second one here. So consider the function f of z. F of z is given by, I'll just write here 1 by 2z. I'll just copy the function 1 by z minus 1 plus 1 divided by 2 into z minus 2. Fine. Since region is less than 2, so I can expand this as 1 by 2z minus 1 divided by, whenever you have less than a number, so you have to take z constant. So let me take z constant, so you will get 1, common, so you will get 1 minus 1 by z minus 1 by 2 common, so you will get 4 here, 1 minus z by 2 you will get, minus 2 common I have taken here, take minus 2 common, so you will get this. Fine. If you want, you can write it in 2 steps. Minus 2 I have taken common in third term. I am repeating once again, minus 2 I have taken common in third term, that is this term. You will get this expression. 2 into minus 2 is minus 4. So plus will become minus and 2 will become 4. Fine. Now you can note that in the first case what we have is 0 less than mod z less than 1 for a given problem. So that is the reason I have taken nothing as common here. That is 1 I have taken common, and here also 2 I have taken common. Here also we have the same thing, that is mod z less than 2. So that is why I have taken constant as a common here, but I have taken z as a common. Why? Because here the condition is mod z greater than 1 here. So whenever you have a term with reference to 1, you have to take that term as a common factor. Fine. So 1 by 2z as it is. Now I can write this as minus 1 divided by z into 1 minus 1 by z power of minus 1. Similarly minus 1 by 4 as it is. So 1 minus z by 2 power of minus 1. Fine. Now you can expand this 1 by 2z as it is minus 1 by z as it is. Now you expand 1 plus 1 by z plus 1 by z square plus so on. Minus 1 by 4 into, now you can expand this 1 plus x square form. Fine. So on you will get. Now if you want, you can simplify by taking the common factor, otherwise you just leave it here itself. So f of z is this. Everything depends on, you have to take care of common term, which term that you have to take, you are going to take a common. So here you are going to take z common. Why? Because at mod z greater than 1 is given. Since mod z is less than 2 is given, so that is why constant is taken outside. So the term which is with reference to less than, you have to take the constant. The term which is with reference to greater than, you have to take z as a common. So this will be applicable for all. So you can go through that. So this is what the second solution. Now third one I'll just do here. Third one is mod z greater than 2. So it is almost greater than 2. So you have to take z as a common. Just by looking at the expression we can decide. See here in this expression you have less than 2. So that is why you have taken 2 as a common. Now you have greater than 2. So you should take z as a common term. Fine. Now let me write the function f of z. It is common for all the functions. Problems. 3 sub questions. Z minus 1 plus 1 divided by 2 into z minus 2. Fine. Now as I already said, it is greater than, so you have to take z as a common term. So let me take z as a common term. You will get 1 minus I'll just take in the function value you have minus, so let me take minus as a common term, or else if you want I can write it in one more step. I have taken z as a common, so you will get 1 minus 1 by z plus 1 divided by 2 into, I'll take z as a common, so you will get 1 minus 2 by z. Clear? Now I can write this as 1 by 2z minus 1 by z into 1 minus 1 by z power of minus 1. Similarly plus 1 by 2z into 1 minus 2 by z power of minus 1. Now 1 by 2z as it is, minus 1 by z as it is. Now 1 plus 1 by z plus 1 by z square. Standard expression I have written. Fine. Similarly plus 1 by 2z into 1 plus 2 by z plus 2 by z square plus so on. So this is what we have. Clear? If you want you can multiply this term inside and you can rewrite. I'll just write one more step. So f of z is equal to 1 by 2z minus I'm not going to multiply, I'll just multiply 1 by z here. 1 by z plus 1 by z square plus 1 by z cube plus so on, plus 1 by 2z I am multiplying inside, so you will get 1 by 2z plus, when you multiply 1 by 2z, see here 2 by z you have, into 1 by 2z you are going to multiply, 2 get cancelled, you will get 1 by z square. Fine. Again 2 square in the sense 4 divided by z square, you will get 4 by z square into 1 by 2z. So 2 1s are 2 2s are, so you will get 2 divided by z cube plus so on. So this is the required expansion of a given function. Hope so it is clear for you. So this is the first problem, first sub question solution, and this is the second sub question, and this one is third sub question. Hope so it is clear for you. So this completes the problems on Laurent series. Now let me explain the next concept. Next concept is periodic function. you have some definitions here. So periodic functions in the sense, suppose if you are going to consider any complex function which is of the form w is equal to f of z, and this function is said to be periodic with a period c. Fine. A function that is a complex function w is equal to f of z is said to be a periodic function with a period c if it satisfies the condition f of z plus c is equal to f of z for all z. I'll just repeat once again. Any complex function w is equal to f of z is said to be periodic function with a period c if and only if it satisfies the condition f of z plus c is equal to f of z. That is, if it satisfies this condition, we say this function is a periodic function. I'll give you an example for this function. Suppose if I'm going to consider a function sin z and cos z. And let me take one more function, it is e power of z. Then let us consider f of z plus e power of I theta. Or f of z plus I theta, I'll just consider f of z plus I theta. Fine. Now it is of the form f of z plus c in the sense period, here period c is I theta. I theta is a period. Fine. So if you are going to consider that for this function, I will just explain. So e power of z is replaced by, since f of z is e power of z, so z is replaced by z plus I theta. Right. So I can write this as e power of z into e power of I theta. Clear? Suppose if theta is equal to 2 pi k, where k is any integer, either you can take k as 0 or plus or minus 1 or plus or minus 2 or plus or minus 3, whatever may be the values of k you give, then e power of I theta can be written as e power of I into 2 pi k, right? Theta is replaced by 2 pi k. So I can write this as e power of I theta expansion, you already know, it is cos theta plus I sin theta, right? So similarly, e power of I into 2 pi k can be written as cos of 2 pi k plus I into sin of 2 pi k. Fine. Then c is, as I already told you, if this was the case, I can clearly say c is equal to 2 pi k is a period. Period of a function. Meaning is f of z plus c can be written as e power of z plus I into 2 pi k. This is what I have, right? So in place of c I have I theta. So I can write this as something like this. So again you can write like this, one and the same. So if this was the case, I can express this as e power of 2 pi I k. Before that, note that whatever may be the value, e power of I into 2 pi k is 1. If you simplify this, you will get the answer as 1. So this term become 1. Meaning is f of z plus c is e power of z. But what is the function we assumed? F of z. Since f of z value and f of z plus c value both are equal, so it satisfies the condition f of z is equal to f of z plus c. So this function is an example for periodic function. I'll just repeat once again. Periodic function is none other than, if it satisfies this condition, we say the function is periodic. Now let us consider the example f of z is equal to e power of z. What I have done is I have replaced it with a period. First I have replaced it with period I theta, and I have given one particular value 2 pi k. So if I give 2 pi k in place of theta, I can express this as e power of z into e power of I into 2 pi k. If you want, you can simplify this, you will get the value as 1. So if this expression 1, I can write f of z plus c is e power of z. Now you can compare these two forms. We can say that f of z is equal to f of z plus c, where period c is equal to 2 pi k. Since it satisfies the definition, so this is an example for periodic function. Clear? Next definition is connectedness. Fine? Connectedness. So any subset, suppose if I have a complex plane, and any subset of this complex plane D is said to be connected if any 2 points, if you are going to consider any 2 points, say z0 and z1, which is in a D, that is, suppose if z0 and z1 is in this D, which is subset of a complex plane, if there exists a continuous map, this is a standard definition. So if there exists a continuous map, say mu from closed interval 0, 1 to D, such that mapping of mu with respect to 0 is z0 and mapping of mu with respect to 1 is z1, and moreover this mu of 0, 1 will be subset of D. This is subset of D. Then mu is called an arc in D. Mu is called an arc in the region D from Z0 to Z1. I'll just repeat once again. Suppose if I have a complex plane C and D is subset of C. Why? Because D is smaller set compared to C. Then if you're going to consider 2 points Z0 and Z1 inside D, then there exists a continuous map mu from closed interval 0, 1 to D such that mu of this mapping 0 maps to Z0 and mu of with respect to 1 maps to Z1 in such a way that mu of 0, 1 will be subset of D, where mu is called as an arc of D. Then D is said to be connected in a complex plane. Fine. So this is the definition of connectedness. Next definition is branch of log Z. A branch of log Z. Meaning is, suppose if I have any open connected set in a complex plane. Suppose G, let us consider G is a open connected complex plane. Then if I have a function f of z in a complex plane, that is open set, then e power of f of z is equal to z. If this condition holds, then f of z is called as branch of log z. I'll just repeat once again. Suppose if I have an openly connected complex plane G and there exists a function f of z in this complex plane, if this function f of z satisfies the condition e power of f of z is equal to z, then we can say f of z is a branch of log z. Branch of log z. Fine. Now let me prove one theorem which gives the relation between radius of convergence and Taylor series expansion. So heading is not mentioned anyhow. So when you read the statement, you will come to know that this gives the relationship between radius of convergence and Taylor series expansion. Fine. So here is the theorem and it is important. It is asked in one of the year. So the theorem says that let f of z is, this is power series expansion in the disk, mod z minus a is less than r. When r is the radius of convergence of a power series, if r is the radius of convergence, then Taylor series expansion of f of z in the neighborhood of a point a is exactly the given power series. So we have to prove if r is the radius of convergence, then the Taylor series expansion is exactly equivalent to power series. Fine. So that is what we have to prove is. In the sense, first we have to consider a Taylor series expansion and we have to show that the Taylor series expansion is same as power series expansion at its neighborhood. In the sense, the point just near to any point z0 in a complex plane. Fine. Now coming to the proof, let us consider a given function, given series, given f of z is equal to summation n is equal to 0 to infinity. Don't worry, all the definitions will be given, only problems will not be given. So you have to copy from the video. All these definition and the theorems will be, notes will be given of the same. So I have considered the what we say function f of z, and the disk is given. Disk equation is mod of z minus a is less than r. Now we have to consider a Taylor series expansion by Taylor series expansion. What is the Taylor series expansion says? F of z is equal to summation n is equal to 0 to infinity f power of n of a divided by n factorial into z minus a power of n. And we have already proved this theorem also. If you want, you can go through the previous video. I have proved there clearly. Now what we have to prove is this Taylor series expansion at its neighborhood of a function exactly gives the power series expansion. In the sense, we have to prove that an is exactly equal to whatever an you have, that will be equal to f power of n into a divided by n factorial. See here, if this term is equal to an, what is this expression become the power series, right? See, what I am trying to say is this is the power series expansion. This theorem says that if you are going to consider Taylor series expansion as it is differentiable at its neighborhood, this represents a power series. In the sense, what we have to prove is this term is equal to an. If this is equal to an, what this expression become? An into z minus a power of n. Again, this is the power series, right? So it is enough to prove that an is equal to f power of n of a divided by n factorial. This is what we need to prove is. Fine. Now given function, I'll just write once again. F of z is equal to n is equal to 0 to infinity an into z minus a power of n. This is the given function to us. Now what I'm going to do is I'll just differentiate one time. F dash of z, I'll just differentiate the given function. And remember, when you're differentiating, it is always with respect to z only. Fine, why? Because it is a complex number. So when you differentiate, you will get n is equal to, the minute you differentiate, the n value changing to 1. 0 to 1 I have changed. Now let me differentiate. A n is constant as it is. So differentiate this n into z minus a power of n minus 1. Now again differentiate once again, that is f double dash. So n value changing from n is equal to 1 to 2. So 2 is equal to, n is equal to 2 to infinity. A n into, now n as it is, now let me differentiate n into, that is n minus 1 into z minus a power of n minus 1 of minus 1, it will become n minus 2. Again let me differentiate 3 times, that is f triple dash is equal to, n changes to 3 to infinity, a n into n minus 1 into n minus 2 into z minus a power of n minus 3. So if you keep on differentiating this term, I'll just continue here. So you will get at particular, say, k value, that is if you differentiate this expression k times, you will get f differentiating k times of z will be equal to n is equal to k to infinity, a n as it is. So this term n into n minus 1, n minus 2, so this will be keep on continuing up to k plus 1 times into z minus a power of, this n minus 3 will become n minus k. I have generalized this differentiation for k number of times, that is if n is equal to k. Fine. So I can write this as f power of k of z is equal to ak, n replaced with k, into k factorial. This is the expansion of n factorial expression, but instead we have k here, so I can write this as k factorial. Fine. Now when you replace n is equal to k in this expression, see here, I'll just replace n is equal to k, how this expression comes. So ak into k minus 1 into k minus 2, so on, k minus k, minus of minus is 1. Minus plus into minus minus, so z minus a power of k minus k you will get. Fine. So this expression is ak into k minus 1 into k minus 2 up to so on, you will get minus 1. So z minus a power of 0. So this expansion is k factorial. Ak into k factorial, anything power of 0 is 1. So this is how I have written here. Now what I'm going to do is I'll just replace z is equal to a. So this expression become f power of k of a is equal to a power of k into k factorial. So I'll just extract the value for ak. F power of k of a divided by k factorial, that is f differentiated k times. Now since k is arbitrary, I can replace k with n. So I'll get a n is equal to f power of n of a divided by n factorial. Meaning the Taylor series expansion become. Therefore Taylor series becomes f of z is equal to summation n is equal to 0 to infinity. So I can replace this value with an into z minus a power of n. So this is the power series expansion, right? This is power series expansion. Hence the proof. That is what we needed to prove is, whatever the Taylor series expansion we have, we need to prove that will be exactly equal to the required power series. We have considered the Taylor series and we have proved that if we can change the Taylor series as power series. So hence the theorem. Hope so it is clear and it is important and quite simple. You can practice. Fine. So this is first page. Anyhow, I'll send you the notes. Don't worry. And the next concept is zeros of, it is important. Next concept is zeros of an analytical function. So you have already learned the concept of analytical function. So a function f of z is said to be analytical if it is differentiable at its neighborhoods z and z naught, right? Now zeros of analytical function in the sense, suppose if I have a function f of z which is analytical, as you already familiar with analytical function. Suppose if this is analytical function in a open set G, suppose if G is a open set and if f of z is analytical in this open set G of a complex plane, then for any point A in a complex plane C is said to be, if this point is said to be 0 of this function, I'll just repeat once again. Suppose if you have a complex plane, that is open set of a complex plane G in a complex plane, I'll just repeat once again. Suppose if you have a open set G in a complex plane, and if f of z is analytical in this complex plane, and any point A in a complex region is said to be analytical, any point A is said to be 0 of this analytical function only when f of A is equal to 0. Meaning is when you replace z with A, the value of the function goes to 0. Then only we can say A is a 0 of this analytical function f of z. Fine. Any value A in a complex region is said to be a 0 of analytical function f of z only when we replace z with A, that is the function value should goes to 0. Then we can say A is a 0 of this function f of z. And the definition for region is a open connected set in a complex plane. Whatever may be the complex plane you are going to consider, any open connected set is called as a region. Open connected set is called as a region of a complex plane. Fine. So this is the meaning of zeros of analytical function. Now let me solve one theorem based on this analytical function. So, and it is also important. So here is the theorem. It is important. It is asked in the year 2018. Fine. So let f of z is analytical in the region D of a complex plane. Then we have to prove that the following statements are equivalent. That is, f power of n of A is equal to 0 and f of z is equal to 0 in the neighborhood of A, and f of z is equal to 0 in a region D, and A is a point in a region D. Fine. So we can prove this statement in the sense equivalent, in the sense first we have to consider a first statement and we have to show that first statement implies second statement, in the sense if f power of n of A is equal to 0 at a point A belongs to D, then we have to prove that f of z is equal to 0 in the neighborhood of A. Similarly, we have to consider second statement true, that is f of z is equal to 0 in the neighborhood of A, then we have to prove that f of z is equal to 0. Similarly, third implies 1 we have to prove. Fine. Equivalent meaning is we have to consider the first statement and we have to show that second is also true. So let me prove that. We have to consider first is true. That is, for any point A belongs to D, fn of A is equal to 0. Fine. Since D is open set, as I already said, D is open set and a point is in, that is a point belongs to D, then there exists a neighborhood of K, any point say K of a point A. In the sense, suppose if I have a D is a analytical in a region, D is a openly connected set in a complex plane. D is always a open set. Fine. Then there exists a point K in this region to the neighborhood of A. That is, if I have a point A here, just beside an A, this point K exists such that this K will be subset of D. Why? Because K is always inside the D. So I can write K is subset of D. Fine. And if Z is any point in K, we can say by Taylor's theorem, let us consider a Taylor's theorem expansion. Taylor's theorem, what it says, f of z is equal to n is equal to 0 to infinity f power of n of A divided by n factorial into z minus a power of n. Right? Therefore, I can write f power of n of A is equal to 0. That is, meaning is this function is analytical. That is, it is differentiable. Therefore, its nth order differentiation will be equal to 0. So, I can write f of z value is equal to 0. And this holds for all z belongs to K. Fine. And it is quite simple, and this is what we need to prove is, see here, A is arbitrary point, so we can replace it with Z. So f of Z is equal to 0 in its neighborhood of A. Fine. So I have assumed that first statement, that is f power of n of A is equal to 0. Why? Because f power of n of A is 0, we have already assumed it is true. So if f power of n of A is 0, if you replace f power of n of A is 0, so this value, entire value will become 0. So f of Z is equal to 0. Simple. See here, first statement is f power of n of A is equal to 0. What I have done is I have considered Taylor series expansion. I have replaced f power of n of A as 0. So if this value is 0, total expression value will become 0. That is f of z is equal to 0. We have proved that second statement is also true. Clear? Now we have to consider second statement is true. We have to prove third statement is also true. That is, we have to assume f of z is equal to 0 in its neighborhood. Of A. Then we have to prove that f of z is equal to 0. So given that f of z is equal to 0, right? So if f of z is equal to 0, we can say if you are going to f power of n of A is also 0. Why? Because we have already proved in the first case that if f of z is equal to 0, then f power of n of A is equal to 0. right? So I can write if f of z is equal to 0, we can write f power of n of a is equal to 0. Right? Now let us consider a set A in such a way that it contains set of all the points in a region D whose mth derivative, that is m power of f power of m of z is equal to 0. Clearly this A is non-empty set, right? Why? Because we have certain elements in this set. Fine. Now let me consider a set B such that which is difference of D minus A. What is the meaning is, suppose if I have a region D, I have considered a set A and this B region is difference of D minus A. Right? I can write this B as D minus A. If you subtract this region from D, you are going to get the region B. Right? So I can express this B as D minus A. Fine. Clearly A and B are disjoint in the sense there is no common point. Disjoint meaning is, as per the set theory, there is no common element in the, remember, any two sets are disjoint meaning is their intersection will be equal to null set. That is, there is no common element between those two sets. Fine. So here also A and B are clearly disjoint sets. And A union B, that is, if you are going to combine these two regions, that is A and B, what you are going to get? If you combine these two regions, you are going to get a region D. Fine. Now we need to prove both the sets A and B are open sets. So as you already studied these concepts in your other subject, that is in real and topology, that we have to prove that A and B are open sets, right? So in order to prove they are open set, let us consider a neighborhood point, say Z0, any point Z0 belongs to K. Then we can write f power of n of Z0 is equal to 0. This holds for all n. The concept is quite abstract. No way, you have to practice. So if that was the case, then there exists another neighborhood such that K1, if Z0 belongs to K and if it satisfies this condition, then there exists another neighborhood K1 of Z0 such that K1 is subset of D and f of Z is equal to 0 in K1 also. Fine. This is for generalized case f power of n of Z0 is equal to 0. As I already proved, f power of n of A or Z is equal to 0. F power of Z is also equal to 0. And that will be holds good for K1. So therefore what can I write as? I'll just continue here. Therefore I can write f power of n of Z0 is equal to 0 also holds. If f of Z is equal to 0 holds, then we can write f power of n of Z0 is equal to 0 also holds as per the first proof. Fine. Therefore, I can write K1 is a subset of A, or I'll just write it in statement symbolic form. K1 is subset of A. This implies that what we have proved is Z0 belongs to K1 and further K1 is subset of, I'll just write here, Z0 belongs to K1. What I have assumed is Z0 belongs to K1 and this K1 is subset of A. Meaning of this is A is an open set. A is open set. So now let me continue the same procedure and let us prove that B is also open. Fine. Suppose if B is not equal to null set, then there exists some point Z1, say since Z0 we have already chosen, say Z0 in B, then we can write f power of K0 of Z0 is not equal to 0. Obviously it is not equal to 0. Why? Because as it is 0 in a set A, right? See here, I have already written f power of n of Z0 is 0 in A, so it cannot be 0 in B. Why? Because f of Z is analytical. Since f of Z is analytical, meaning is f of Z is analytical in the sense if you are going to consider 2 points in a complex plane Z and Z0, if f is differentiable at Z point, it is also differentiable at its neighborhood point. That is, it is differentiable at Z0. That is, it is successive derivative is also analytical. See here, if f power of K of Z is differentiable, I can write f power of K1 of Z0 is also differentiable. If it is differentiable at one point, it can be differentiable at other points as well. So that is the different meaning of analytical is. Therefore, I can write f of K0 of Z1 is a analytical function. Analytical function in region D. So if this is analytical region, every analytical function is continuous, right? So thereby, but by that theorem I can say f power of K0 of Z1 is continuous. And further this value should not be equal to 0 and hence we can find another neighborhood, say K2. Why? Because we have already chosen K1 as a neighborhood of A. So let me take K2 as a neighborhood of point Z1 such that K2 will be in the region, same region D. And now f power of K0 of Z1 is also not equal to 0 as it is not equal to 0. See here, if particular property holds good at a point Z, it will be true for at its neighborhood. as per the property of analytical, since if it is not equal to 0 at z0, it cannot be equal to 0 at z1 also. Fine. Then let me take z1 at the point k2 such that z1 belongs to B. Then for every z1 in k2, k2 will be subset of B. Or else I can write it in a statement form that z1 belongs to k2 and k2 is subset of B. Meaning of this statement is B is open. As we already done it for A, similarly we have done it for B is open set. So what we have proved is A and B are open. Now we can express D as union of A and B. See here, we can write D as union of these two sets only when A and B are open sets. So that is what we have proved. A and B are open, therefore I can express D as union of A and B. Then A should not be equal to null set and B should not be equal to null set. Fine. If D is connected, then only B will be equal to null set. Fine. Implies D is equal to A. If, I'll just repeat once again, if D is connected in such case, B can be equal to null set. So if B is equal to null set, D is expressed as purely A. Implies that f of z is equal to 0 in D. F of z is equal to 0 in D. So what I have assumed is equation 2 is true, that is f of z is equal to 0 in neighborhood of A. What I have proved is f of z is equal to 0 in the region D, and that is what we require to prove is I have assumed the second statement is true, that is f of z is equal to 0 in neighborhood of A. I have proved that it is true at the point D, that is fourth statement. Third statement, I have assumed second statement is true, f of z is equal to 0 in neighborhood of A. I have proved f of z is equal to 0 in D. That is third statement I have arrived. Clear? First case I have proved, taken first statement, I have proved second is true. Second I have assumed it is true, I have proved third is true. Now reverse, I have to prove third is true, I have to prove first is also true. That is, let us take third statement is true. That is, if f of z is equal to 0 in the region D, then we can directly write that f power of, if f of z is equal to 0, f power of n of z is also 0. In particular, f power of n of A is also equal to 0. That's all. That is what the first statement is. Fine. What is the third statement? F of z is equal to 0 in a region D. Now we need to prove that first statement is true. First statement in the sense f power of n of z. F power of n of A. See, third statement f of z is equal to 0. If it is equal to 0, it will be generalizing case. F power of n of z is also equal to 0. In particular, let me replace z with A. So you will get f power of n of A is equal to 0. So equation third implies 1. So theorem is quite abstract. Hope so it is clear for you. Anyhow, I'll send you the notes. You just practice it. It is important as it is asked in the year 2018. And anyhow, we have 3 more corollaries based on this theorem. And it is very lengthy. So you just practice this theorem. And those 3 corollaries I will be doing in the next session. Thank you.